Hello everybody. So my name is Parnia and I'm from RWTH Aachen University. Let me note that this talk would include some technical terms, so please feel free to ask the questions if you have any. In this talk, I'm going to talk about hidden Markov model, HMM factorization in neural machine translation, which is one of our ongoing work. And as an introduction, I'm completely sure all of you know what machine translation does. So machine translation aims to translate sentences from one language, which is source language, into target language without any human interaction. And for this purpose, let's assume we have a given source sequence F1 to J of length J, which is known, and a target sequence E1 to I of length I. And in this case, we define the posterior probability distribution as you can see here, as a conditional probability, P of the target sequence given the source sequence. So still, I think as literature and many research works have shown, word alignment is a crucial component for machine translation systems. It's really important to define a really good correspondence between source and target words. So we can just model alignment information either explicitly or implicitly. For example, in statistical approaches like traditional phrase-based systems, hidden Markov models approach or IBM models ones have been widely used to just build the word alignments explicitly. While in attention-based models, as well as recurrent encoder-decoder attention architecture, transformer, or convolutional-based neural machine translation, we have an attention weight which selects the source positions while we generate target words. So we can consider this attention weight as a probabilistic notion of alignment, which is a kind of implicit model inside our translation model. But many research work show that it does not work the same way as the alignment models in phrase-based system, and this attention weight doesn't influence the final translation scores because we just implicitly have this alignment distribution as an intermediate steps in our translation model. So in order to bridge the gap between the promising or let's say successful approaches in phrase-based system and attention-based model, we propose a novel, let's say, approach to mimic the behavior of the hidden Markov model-based alignments. To do so, we just follow the direct HMM factorization and we try to integrate it into attention mechanism. We don't have any explicit HMM features. The network is completely a single network and it's end-to-end training. And in this case, we can have a separate translation score for every target source word pair. So I'm going to just talk about it later. Okay, to begin with, I'm going to review attention-based model because this is my starting point and the proposed model is based on attention model. And then I'm going to talk about the new architecture. So again, attention model is just a state of the art right now in neural machine translation, and we translate one language to another using a single and big neural network. And the input and output are just variable length sequences due to using recurrent neural networks, especially LSTMs. Encoder reads the source sequence and encodes it to a set of vectors, H1 to Hj in our case. And then using a weighted sum of these vectors, we decide which source positions would be the most important and relevant position for our translation. And therefore, it learns to align and translate at the same time. So if we want to formulate everything, let's say the attention mechanism has two LSTMs, the bidirectional encoder, One LSTM encodes the source sequence from left to right, another from right to left, and then we concatenate these two vectors to have a final representation of our source words. And then while computing the target words, we have an attention layer, which is dependent on previous target words and all of the source positions. We have a softmax to get a probability notion of alignments. And these attention weights are used to calculate the context vector C of I. This context vector is just weighted sum of encoder representation, as you can see here. And we use this C of I as the only vector which includes the source information while we do decoding. And using the chair rule, we can define the posterior probability distribution of the target sequence as here. It is dependent on previous target words and the entire source words. So how we just use this formula or equation to propose a new approach. In a new approach, which is based on indirect hidden Markov model as approach, we defined exactly similar to direct HMM approach, where the word alignments is a hidden variable, and it is defined from target I to source J. We do exactly the same. We introduce variable J as a hidden variable to our posterior probabilities, and then decompose this distribution into two parts. The first part is alignment model, and the second part is lexicon model. Here you can see when you introduce this J variable, you have sum over J positions, and then you can decompose these probabilities to two parts. The first one is alignment model, and the second one is just lexicon model, as like direct HMM approach. I'm using different notation which use LSTM representation. As you know, LSTM encodes the target histories to our decoder state Si-1. And in the encoder, we have bidirectional LSTM, which encodes the whole source sequence to H1 to J. So keep in mind that having previous equations, you can just rewrite these equations using LSTM representation. It's just a sort of notation. Nothing is new here. And here you can see, in order to calculate the alignment model, we have dependency based on all J positions, which is HJ, and Si-1, which is the previous decoder state. These dependencies are exactly the dependencies which we use in our attention layer. Therefore, here we can simply use attention weights as our alignment model, because it can be considered as a probability distribution. So the difference is that we need to calculate lexicon model for each J position, because in attention mechanism, we have just a vector, and we just use this vector to calculate the whole translation model. But here, we need to calculate this lexicon model J times. So we need to calculate softmax J times over all source positions, and for all source positions over target vocabulary. And yes, here just attention base serves as alignment probability, and we need to calculate the lexicon model. This figure shows you a really simple illustration of the difference of these two models. The left one is the attention model. Here I want to show that, okay, in order to calculate your scores, you have dependency on EI-1. I think you cannot read it. It's really small. Si-1 and the whole source sequence, which is come from C of I. But in this figure, we need to calculate J different scores for each J position. This is just a kind of illustration how these two models can be different. We can just say the main difference between these two models is just the level of averaging. And let's see some experiments. We carry out our experiments for 3 WMT 2017 translation tasks. The systems have been built using our in-house implementation of NMT approach, which is based on Block and Tiano. But unfortunately, Tiano has been not developed anymore, so we need to switch to some other frameworks. Yeah, we carry out the experiments on German, English, and English, German translation task, which consists of 4.6 million samples, and Chinese to English, which is extremely huge with 23 million samples. And then we applied byte pair encoding to split the words to the smaller parts, subwords, with 20K, 20,000 operations. And we use 620 dimensions for our embedding and LSTM nodes with people connections using 1,000 cells. And we use Adam optimizer as our optimization and drop out of 30%, and the final model is just the average of 4 best snapshots of a single training run. And we evaluate our models based on case-sensitive BLEU and 3R, which is computed by these two tools. Here you can see some of our translation results for these 3 tasks. As you can see, for all of these test sets, we use, just let me add, for German English and English German, we use News Test 2015 as our def set, and News Test 2016 and 17 as our on-scene test sets. For Chinese, News Def 2017 as def set, and News Test 2017 for test. And here you can see we got some improvements for all of these tasks. For German to English, 0.5 BLEU and 0.8 of TR. For English to German, 0.6 BLEU and 1.1 percentage of TR. And the biggest gap is for Chinese to English with 1 BLEU and 2.1 percentage of TR. We believe that this lexicalized alignment model assigns proper or appropriate scores for the target and source word pairs. Another issue, which is really important, is speed, based on the fact that we employ a softmax layer over target vocabularies to calculate lexicon scores J times for each J positions. The proposed model is slightly slower than attention. For example, here you can see the comparison during training. For German to English, attention model needs 0.26 seconds per batch, but the HMM-based model needs around 2 times, 0.47 seconds per batch. And here, based on the fact that we just take a kind of baseline which we know it works reasonably well, and we didn't want to just advance the state-of-the-art approaches. We show the results, but this approach can be incorporated to any approach, like any architecture like transformer or CNN-based neural machine translation. And one can extend both lexicon and alignment models with more dependency. For example, we assume that all of our dependency for the alignment model is zero-order dependency. If we want to calculate the attention weights, we don't have any information from previous attention weights. We don't have any coverage, but someone can just include this information as well. And in order to speed up, one can sample from the alignment distribution. For example, take the top 10 best or top K best source positions and calculate the corresponding lexicon probabilities only for these positions. This approach can maybe speed up the whole training and decoding, because there is no need to calculate softmax for all of the J positions, only for top 10 K. I think that's it. Thank you.
Any questions?
What do you think is the reason that HMM-based methods, outperform attention methods?
Okay, yeah, we just show some experimental results, but the point is that our motivation was to bridge the gap between attention mechanism and successful approach of alignments from phrase-based system, because HMM-based and IBM models have proven to be really successful for statistical approaches. And in attention mechanism, we don't have any explicit alignment information. When you have this weighted sum, you don't have any alignment information anymore. I mean explicitly. So we just thought about why not having alignment information and lexicon information separately, and then multiply them, sum over J position, normalize, and then do just scoring in a different way, like direct HMM approach. We did some experiments, and then...
So do you think the reason is that it has better generalization ability, or is...
not generalization. I personally believe that in this approach we have a more structured alignment model, because we have lexicon information which is combined with alignment information, which maybe give us a better score. It is a kind of more structured way to define the correspondence between source and target.